Okay, questions 4A through 4D for Chapter 3 in An Introduction to Statistical Learning. So the idea here is that we have some data that we fit two different regressions to. One is a cubic regression that there's one predictor variable, but we use, and it's x, and we use x as well as x squared and x cubed. So this is the cubic model. As well as a linear model, which just has x, right? So x isn't being raised to any exponent here, all right? And we're asked a few questions about these two different models. So the first question is, suppose that the relationship between x and the outcome y is actually linear, right? That data actually would be well modeled by something like the linear model, okay? And now consider the residual, the sum of squares, or the error measurement, when we fit this model for the training data. Which of the two regressions would we think has a lower error, or a lower RSS? The linear model or the cubic model? Okay, so right away this can be a little bit tricky because we're saying that the true relationship is linear. And so we might think that the linear model will fit the training data better. But this probably is not going to be the case because that data, remember, has error, and that error is represented with this epsilon term. Okay, but if we do go to fit a cubic model to it, these additional terms, the beta 2x squared and beta 3x cubed, those are going to detect, well, it's hard to say that they detect if it's not really there, but they are going to imagine that they detect, if we're going to humanize it a little bit, patterns of x squared and x cubed that are actually just noise. The extent to which the noise matches the patterns represented by the additional terms will just be coincidence in our given sample, but nonetheless, the more complicated model will fit it better. So the residual error will be greater with the linear model than with the cubic model, even though the data actually is linear. Okay. Now, in B, we're asked to consider the opposite of that, or I shouldn't say the opposite. We're asked to consider the test data rather than the training data. So now we're looking at new data on which these two models have not been trained. And now which do we predict to have higher or lower error? Well, now it should be the linear model would have lower error in general. Why? Well, the reason, again, is because whereas the cubic model, it was imagining patterns that were actually just noise, those coincidental matchups between the noise and the patterns that model was seeking are not going to be there in the next set. And so the cubic model is likely to make more errors that the cubic model is not making because it never looked for these patterns that did not exist. Okay? So in the language that we've been using so far, the cubic model in this case would be too flexible and therefore would incur more error for being more variable. Okay. Okay. So now in C, we're asked to consider that the relationship is no longer linear, right? And so now we're asked the same questions. Which model is expected to have lower error, the cubic model or the linear model? And once again, it's generally going to be the cubic model for the same reasons, which is it's more flexible, right? And so the nonlinearity in the relationship between x and y is just going to be fitted better by a more complicated model. Okay. And now D asks, what if we look at the training data rather than look at the testing data rather than the training data? Which of these models is likely to fit better? Well, now we don't know. Now it really is an empirical question. It depends on how nonlinear the data is, right? We already know that the linear model is going to be incurring an error because it's biased, right? It can't handle the complexity of the nonlinear relationship. But the question is how much error is it going to incur compared to the amount of error incurred by the cubic model, right? The cubic model could still have too much variance, right? So if it's just if the relationship between y and x is just slightly nonlinear, then the linear model may do better. If it's pretty nonlinear, then the cubic model may do better. So anyway, those are my answers.